Inside a typical stellar mass black hole, the last millimeter before the edge stretches into thousands of kilometers of warped space-time. The closer you get, the more space and time themselves swap roles. Falling inward becomes as inevitable as moving from your past into your future. From far away, a black hole looks like a simple dark sphere. Up close, it's a region where the geometry of reality is so distorted that inside and after stop meaning what you think they mean. So what's really inside that darkness? To answer, you have to let go of everyday intuition. A black hole is not a cosmic vacuum cleaner, and it's not a solid object. It's mostly empty space, ruled by gravity so intense that even light cannot escape once it crosses a certain boundary. That boundary is the famous event horizon. For a black hole, with the mass of our Sun, the horizon would be only about 3 kilometers across. For the monster in our galaxy's center, Sagittarius A star, it's about 24 million kilometers wide, roughly the orbit of Mercury. From the outside, you can completely describe a simple black hole with just 3 numbers: its mass, its electric charge, and its spin, or angular momentum. This is the no-hair theorem of black holes. All the messy details of what fell in, stars, gas, planets, even you, are erased from the outside view. Only those 3 properties remain. The event horizon is not a surface you could bump into. It's a point of no return in space-time. Cross it, and every possible path you can take leads inward. Not because you're being pulled, but because inward has become the only future you have left. To understand the interior, imagine space-time as a landscape. Far from the black hole, the landscape is almost flat. As you approach, it dips into a steep valley. The event horizon is where the valley becomes a waterfall. Outside, you can still climb out with enough rocket power. At the horizon, even light moving at 300,000 kilometers per second can't climb back up. Inside, the downhill direction isn't just where gravity points, it's where time points. Every second that passes pushes you closer to the center. The singularity, just as surely as every second right now, pushes you from your childhood toward your old age. If you fell in, what would you experience? For a small black hole, with a mass a few times the Sun, you'd be torn apart by tidal forces well before you reach the horizon. Your feet would feel much more gravity than your head. The difference would stretch you into a long, thin stream of matter, the famous spaghettification. But for a supermassive black hole, millions or billions of solar masses, the horizon is so large that the gravitational gradient there is gentle. You could cross it without noticing anything special locally. Your clock would tick normally. Your heart would beat. You'd feel weightless, in free fall, drifting toward the center. From your perspective, you fall in and cross the horizon in a finite time. From the perspective of a distant observer, watching with a telescope, you never quite make it. Your image slows, redshifts, and fades as the light from you loses energy climbing out of the gravitational well. This isn't an illusion, it's a consequence of general relativity. Time really does flow differently in different gravitational fields. The interior of a black hole is a region where the direction we call toward the singularity is as unavoidable as toward tomorrow is for you right now. There is no hovering, no orbiting, no turning around. Mathematically, the simplest black hole interior ends in a singularity, a point where density and curvature of space-time become infinite, and our current physics breaks down. For a non-rotating Schwarzschild black hole, that singularity is a point. For a rotating Kerr black hole, the equations predict a ring-shaped singularity and even exotic regions where time travel might be possible. But these are almost certainly artifacts of pushing Einstein's equations beyond where they can be trusted. In reality, we expect quantum gravity, a theory that unites general relativity with quantum mechanics, to smear out the singularity into something finite. But we don't yet know how. What we do know comes from outside. We see black holes indirectly through their effects. Stars whipping around invisible masses, gas heated to millions of degrees in accretion disks, gravitational waves from colliding black holes rippling through spacetime. The Event Horizon Telescope has imaged the shadow of a black hole, the dark silhouette of the event horizon against glowing plasma. These observations match general relativity's predictions with impressive precision. That gives us confidence that the exterior description is right, and the interior, while hidden, is governed by the same underlying geometry. But the deepest question is not what's at the center, it's what happens to information. According to quantum mechanics, information, the detailed state of matter and energy, can never be truly destroyed. According to classical black hole physics, anything that falls in is lost behind the horizon, and when the black hole eventually evaporates via Hawking radiation, it should disappear entirely. Stephen Hawking showed that black holes radiate like hot objects, very slowly shrinking over unimaginable timescales. A solar mass black hole would take about 10 years to evaporate. But Hawking radiation seems to carry no memory of what fell in. This is the black hole information paradox. Either quantum mechanics is wrong, or our picture of black hole interiors is incomplete. Many ideas compete to resolve this. Some physicists propose that information is somehow encoded on the event horizon itself, like bits on a holographic screen, and gradually leaks out in the radiation. Others suggest that the interior and the exterior are more deeply connected than we think, through concepts like ER equals EPR, where wormholes and quantum entanglement are two sides of the same coin. More radical proposals talk about firewalls, violent walls of high-energy particles at the horizon that would destroy anything falling in, violating the equivalence principle. None of these ideas are confirmed. They're attempts to reconcile two extremely successful theories that currently disagree about what's inside. So, what's really inside a black hole? As far as our best-tested physics goes, a region of space-time where every future path leads to a central singularity, where matter is crushed beyond our current understanding, and where the usual separation between space and time dissolves. But the true interior, the quantum structure of space-time, the fate of information where the singularities are replaced by something new, remains one of the biggest open questions in science. Somewhere between the equations of Einstein and the equations of the quantum world lies the real answer. And until we find it, black holes will remain the most mysterious rooms in the universe that we can never enter, only imagine, here on Terra Nova.